Uh, okay, so share screen. So is the screen visible? Hello. Okay. Okay. So I'll be covering what active learning is in brief, and then the especially we are concerned with query strategy methods. So how to query? There are some other aspects like stopping criteria and all those. So that will keep fixed. So this is a research report that I submitted uh, in a project, and then maybe we can look at it because it explain the concept very simply. So the steps are for active learning are oracle. That means give you ask an oracle. Oracle is someone who knows everything. The correct the label the oracle knows. Then what you do is you pass the unlabeled instances based on the query strategy. Then oracle labels those and gives to you. You update the model, and maybe or maybe not you update the set of unlabeled and unlabeled points, and then you repeat the process. So to learning machine learning. So this is the process. There's active learning. What you do is you have unlabeled data. You select which one to label using query strategy. Then you give it to Oracle. Oracle will label it. You get a labeled data, and then you retrain the model. And like why is active learning is a very old concept, but why it is uh, okay? Why it is like it why should we study it in the like a recent thing? This is uh, because of deep learning. Like there is very little research in active learning and combined with deep learning. So the two main things are these points, which is that active learning, what it does it needs very low data, like very low percentage of data should be labeled, whereas deep learning needs to learn from a very high amount of data. So combining these two paradigms is a challenge. Another thing is that in deep learning we use neural networks, and neural networks, what the estimates of probability that they offer, they are not very reliable. So but for active learning we need very reliable estimates fast, because we'll be training the model many times. So these are the two challenges. And then there are various query strategies, and the classification is like this: random, informativeness, representativeness, and hybrid. So random is just like you select any random without any query strategy. By the way, you guys have to note the specific methods that I am telling, because note means you have to keep in mind that where they are so that you can implement those. Mm, okay. So that so informativeness, which means that how much information, like there are two main things. For example, suppose you want to give a test, you have to take a test. Okay, okay, let me frame it this way: that you are preparing for an exam. Now you can select either the questions which are most likely to appear in the exam, or you can select the hardest questions and practice. So the ideal approach is a mix of these two, that you will select practice questions that are most likely to come, and also you will consider questions that are relatively hard, because there's no point in practicing easy questions again for the exam that you're about to take. So this is basically the informativeness. and representativeness. And this is also known as uncertainty versus diversity trade-off. So informativeness means that uh, how much information is, the more information, the harder it is to learn. So that will give it the maximum improvement. So output uncertainty. Output uncertainty is one of the method. Like these are the four sub classifications of informativeness: output uncertainty, disagreement, gradient, and performance prediction. So output uncertainty, they can have uncertainty sampling, entropy, least confidence, margin, closeness to SVM decision boundary, and divergence. So I'll be going over each of these again below. Disagreement means that one way was to model uncertainty from the softmax estimates. Another way is to disagreement. Like you can have multiple models, and you can like do a voting system that okay, which models on which data points most of the models disagree. So that you can take. Then there is gradient. Gradient means that change. It is like a slope in the. It's like a slope. Okay. So expected gradient length. What you do is for all you weight the expected change in gradient of the loss function with respect to the probability, and then you uh, the like select the ones. Then performance prediction. This is like kind of similar to gradient, which means that you predict the performance using another model. Now representativeness has uh, can be divided into three parts, like density, discriminative, and Bayes diversity. So okay, first of all, representativeness was the other parameter, which was like how representative the point is to the entire sample. It is like you're selecting the most likely questions which you are going to get in the exam. Now density, so expected loss reduction, discriminative, similarity with respect to n-gram and k nearest neighbors, and batch diversity. So diversity with respect to n-gram, word count, and out of vocabulary. So expected loss reduction is kind of similar to expected gradient length. Similarity with respect to n-gram is like uh, you are select n-gram means like you're predicting for each of the successive prediction, you're predicting the n words and possible predictions. And similarity with respect to n-gram is like similar, which the models, the point that you give is similar n-gram. K nearest neighbors is okay. K nearest neighbors is like you give k points and then you select the k nearest neighbors, and then you the k number of nearest neighbors, and then you go and uh, like select. Okay, I'll be explaining it below. And then batch diversity is kind of opposite to above, like diversity with respect to n-gram, word count, and all. And hybrid is basically combining these two. So weighted sum, you weight each of these parameters linearly. Diverse gradient selection is basically batch diversity and expected gradient length. Detrimental point process and multi-step querying. Multi-step is like querying at multiple steps. So okay, and then we go to like what each of the so this part is like simple. We'll be going with our query strategy. So least confidence is basically now. Uh, okay, maybe some problem with the internet. Let me try hotspot. Hello. Uh, Now it is visible. Hello. Uh, Now, so then we have least confidence. This is basically uh, confidence, the probability of label of the like most likely label for a given data point, which means that in the softmax you select the maximum. Uh, Suppose you have 5 classes, then you will select for each label you will select the maximum probability from the softmax. For example, say class number second has the highest probability, so you'll select that as this value, and then 1 minus that value will be the confidence. So uh, you have to maximize this 1 minus the deviation from it. Okay, sorry, like this is the confidence, and you have to maximize this, which means that you have to find the sample for which the value of the highest probability among all the possible predictions for each class is the lowest. Like maybe it is little tough to tell, but it will be very easy if you think over it. Like why I miss this is the most probable label probability for a data point, and then you have to maximize it this quantity. Now prediction entropy. Entropy is basically P log P and summation over all dimensions. Dimension is the class, number of classes. So for each data point, you find P log P, this entropy, and then maximize it. Now, and the one with the highest entropy will be the one which has highest disagreement among its own values. Uh, Suppose you get a prediction value for say 5 classes, you get all vectors 0.2, then that will be the highest entropy as compared like this the highest quantity as compared to say one of them is 0.9 and the rest of them are 0.025. So this is prediction entropy. Then breaking ties, yeah, margin sampling. Margin is basically computing the difference of the top two predictions for each data point and then finding the maximum value. For example, the the sample which has the difference between the two. mm, I think there is something wrong here. There should be a negative sign. It should be argmin. Negative sign there should be. So like you have to find the suppose there are 2 classes, so that's 5 classes of them like the predictions are very close for the first and second class, then that sample should be learned as compared to the classes where the prediction for the highest like most probable is way more than the next one. So this is margin sampling. Then k means which means that you select for all the data point you select k clusters or you get k clusters of the data point. K means a standard algorithm wherein you supply k and then you get clusters. So k means is a kind of like you get the clusters and then you select from those clusters. Basically, you have to implement least confidence, prediction entropy, and margin sampling. So note down these. Maybe you can like write least confidence, prediction entropy, and margin sampling. I'll give you only those that are very simple to implement. So greedy core set. Core set is a compact representation. Uh, Core set means that uh, okay, how to explain this? Suppose core set is a problem which what courses do is like there is very large amount of data and you have to train the model on that. Core set is basically you convert that entire data into a smaller like a sample of a data, smaller number of points, such that the um, the result that you get after training the model is same as the one that you could have achieved when you had if you had trained on the original model. So that is greedy. That is core set. Uh, Maybe I can show you also. Mm, Core set. Core sets in machine learning. I think I saw a video. Okay, so yeah, like from this figure you can understand there are lots of points. So you are computing a function, like you are giving like computing something from these points, and core set is basically you compute some points and corresponding weight vectors to that, so that when you compute that same function on these new data points with respect to the weight, you get exactly same value. This is core set, and there are various ways to compute it. Then core set, uh, I saw a very nice video on this. Okay, I'm not able to find it. Maybe now. I think yeah, like this is the data heroes thing. So you can watch these short videos. These are like very good. They good a very good introduction of the core sets. And I can also show you the mathematical formulation. So this is the core set formulation. You can watch this video. It will give a very good idea. And essentially, it is the same thing that there are lots of points. You compute a subset of those points, corresponding weight, so that when you apply a function to those, uh, they apply a weighted sum of function, then you get exactly the same result as you would have achieved through normal uh, training on the original set. That is core set. And like there is various methods for this, like lightweight core set and greedy core set. These are like very common. For example, in the light greedy core set, what you do is you add an additive term to this. Uh, Sorry, in the lightweight core set, you add an additive term. So yeah, and BALT, Bayesian active learning by disagreement. This is essentially the same thing, which is like the disagreement, which is like you train multiple models and then you ask them to vote, and the one with the least vote is chosen. Like you have to maximize disagreement. Now contrasted learning. So contrasted learning maximize this quantity KL divergence. Now what is KL divergence? So KL divergence is basically you model you know K okay, KL divergence is used to compute the difference between two uh, distributions. It's something like you want to move one, you want you cut a small portion of each distribution and move to another distribution. You have to form the now how what is the similarity between the two. So it is KL P log. Suppose KL divergence of P with respect to Q is given by P log P by Q, and 1 upon M is, I think, mm, the model dimension. Yeah, so J equal to 1 to M. Mm, okay, so basically you have to maximize this quantity. KL divergence measures the similarity between the two distributions, and contrasted learning, what it does is you have to compare like uh, each distribution. This, for example, the softmax vector you get from each of its m nearest neighbors. So what you can do is, suppose like nearest neighbor, you understand, if you plot each of the points on a higher dimensional space, then uh, the distance between them two can be given as say like Euclidean system. For example, if one point is, say, suppose we have two-dimensional vector 1 comma 0 and 2 comma 5, so the distance will be root of 1 square plus 5 square, the Euclidean distance root. And this thing, contrastive vector learning, what does it? Probability, the label, the probability distribution for the k nearest points, like the nearest m nearest point, sorry, m nearest neighbors, and you compute KL divergence and weight it with respect to m, and you have to maximize this thing. What it essentially means is that uh, if the KL divergence is high, which means that there is a very big disagreement on an average from a point, between a point and its neighbors, then we should learn that point, because model has misclassified it kind of. So yeah, maybe like you can Google KL diver. KL diver is a very useful method. It's very simple to understand, uh, and there are lots of posts on it. KL divergence is basically like you can like, yeah. So like this is a very good post making sense of the KL divergence, and you can read about this. This will explain what the KL divergence is. And once you have KL divergence, you can use simple algorithms to compute m nearest neighbors, or you can do any clustering algorithm also. For example, you can use uh, mean shift algorithm or k means to find the centers, and then you compute the distance from each of the point from those centers. So for the assign, okay, this is the contrast calculation. So you have to implement this also. And to simplify your work, like what I can say is that for each of the point xi, you can use a simple n square algorithm, which means that you compare this point with every other point and the distance, and then you can compute what we can say, the nearest neighbor, like find the nearest neighbors, m nearest neighbors you can find, for example, using a priority queue or something like that in Python maybe. Okay, so these are the four methods that are helpful. Then in this paper also, uh, like essentially these are the simple methods. Then there are complex methods, like it will be hard to implement, so I'm not giving that. But maximum entropy, margin I've covered, least confidence, mean standard deviation also. Like it's simple that from the distribution you compute the standard deviation, and then for all the points over k, and then for all the classes, and then you find the one with mean standard deviation. So maybe you can implement this also, like computing the standard deviation with respect to okay, but how will you compute this? You'll get a distribution, and then you'll get a probability for not a distribution. This will be a little hard to implement, so maybe you cannot ignore this, but you like these are the basic methods. And then core set, k means, cluster that I told you. And like the complex methods are essentially either they differ on the type of model, or for example, generative adversarial active learning using GANs, or they are like either uh, the complex methods, they either use specific models or they use a simple framework. For example, they can be like how to define the vote strategy in the query by committee and all those things. So You can read this for your fun. Like they are too complex to explain. I would have uh, like maybe I'll share some resources if some of you are interested. But like this paper, you can read it from page number 3 to page number 5, 2 pages. It will give an idea, and I can understand that it will be hard to understand most of the concepts. So you can just go over it 2 or 3 times. You just have to get the feel of it. Understanding the exact mathematics, especially for the deep active learning frameworks, is really hard. So then moving on to the third resource. Okay, where is it? So here also, mm, okay, I forgot to mention that there are 3 scenarios to apply active learning. One is pool-based active learning, which means that you have, say, 100 unlabeled samples. Then you apply the method to all of the 100 unlabeled samples and select the one which is suitable according to the query strategy. Then there is stream based, which means that you get data in streams. For example, you get 10 new samples, you do active learning on those. At a later time, when you get 10 more new samples, you do find the best one and then do active learning. The third, okay, this is stream based. Third one is membership query synthesis, which means that you're figuring out like what type of data you want, which will give the best training result, and then you generate that kind of data. So membership query synthesis. Okay. So these are the 3 scenarios. Like for the assignment, it's very simple to implement pool-based active learning. That's the common case also. Then I think I have not explained this density weighing method, density weighted method. So we can maybe go over it. Uncertainty sampling. This is entropy. Okay, you can read this query strategy part from this book also, but and should be simple enough. That will give you an intuitive sense also. Then this is confidence actually, the prediction of particular the largest class is confidence, and you have to minimize this. Then okay, so then there is there is a very small thing here in uncertainty sampling. Uh, there are 2 types. First is based on probabilistic learning models, like the ones that we dealt, least confidence and uh, entropy, all those things. Uh, Another one is based on non-probabilistic models. For example, you can use a decision tree, or you can use each neighbor to vote based on the class label X, or SVMs and all those things. So like this is not needed for the assignment then, but still like you can go over. Active learning is basically very vast. Like it is very generic for any model, any uh, metric. You can derive a query strategy metric. So that's why it makes it so vast. But these things are very basic. And query by committee is essentially the voting thing that I told you, that you have a committee of models which are trained on the label set, but competing hypotheses, which means that they have different weights, they kind of differ, and then they are allowed to vote, and then you select the one with the least vote. So then there are various methods like query by boosting and all those, query by bagging. Two main approaches are the vote entropy, which means that you compute a vote function b, and then compute vote entropy, or you can get KL divergence also. And then this agreement is KL divergence, which is divergence between the average. I think this is the average from the committee, and then this is the current one. So these are the 2 main methods. Essentially, what like This is the composite. For example, we discussed the KL divergence and it applies that to the average of the model. Vote entropy is also similar. So you can derive many frameworks from this. Then expected model change. So like this is something very interesting. And this is kind of a bonus assignment. Like will you implement this expected model change? Expected model change is the same thing as expected gradient length, which means that you uh, okay. So this is gradient, this is loss, and this means labeled sample. And what you do is you add the data point with respect with the label to the labeled set along with model parameters, compute the loss for this combination, and then compute a gradient. Okay, with respect to model parameters theta, you compute and okay, and then what you do is like this is probability y with respect to x and theta, which means for the current model and x, what is the probability that the label is yi, that is the confidence, and you weight along with this. For example, if the class is the model, the data belongs to class 1, what is the probability, and then suppose that it belongs to class 1, then we add this to label sample, compute the gradient, and then you sum it up. This is something like the calculation of expected value. Okay, so you do this, and then you basically another. Okay, so this is expected gradient length. Like I'll be really happy if someone implements this. And be careful that this is the gradient with respect to model parameters. Okay, and another thing is like this thing you can approximate with respect to with this like computing gradient of loss with respect loss on the entire labeled set and the current sample current point is equivalent to loss on only the current point. Okay, then intuition is that instant likely most influence the model regarding, yeah, so like like this is the explanation because like the new point is not the one on which the model was trained. It's from the unlabeled set, so that is expected to cause the most change, so that's why we can exploit this is the uh, expectation. Okay, and variance reduction I told you above also. Fisher information ratio is also similar. Like this is variance, and Fisher information is basically this thing, very complicated looking function. You compute gradient with respect to model, and then for the log, and then you double derivative, and then you compute the probability with respect that the label is y, and then integrate over all y, which is summing, and then you have the probability of x, and then you integrate over x, and then you get information of theta. Mm, like you can go over it, but it's really difficult to implement, and it's similar to like the variance reduction. Estimated error reduction is similar to estimated loss reduction, but here what you compute is you estimate the error using a model, and then you compute the points which is like which can reduce the error with maximum. Okay, now density weighted methods. So this is basically combining uh, the informativeness and uh, uncertainty. No, representativeness and uncertainty. So this is basically the one that we all studied above. One of the methods, the function which leads to uncertainty, which means how hard the sample is. And this is a function which leads to how representative the sample is. And XU is like estimate, which represents the mm, okay, where is XU? Like it's is this XU is kind of a representative of the sample. Like maybe you can take it to like vary for all the samples in the unlabeled set and then average it. As similarity is a function, for example, a similarity metric, like how similar these two vectors are. And maybe you can use any metric, similarity metric for it, for example, cosine similarity, FAS, and all those. So actually, the assignment will be to implement the four query strategies that I discussed, along with like three or four similarity metrics. So similarity metrics, this is very simple. For each of the points in the unlabeled sample, you compute this thing, and these two parts of computation can be done separately also. For example, you can compute this and store. You can compute this and store. This will reduce the overall complexity, and you can implement this. Also, there's a beta parameter. For example, how much weight you want to give to the representative thing. If beta is zero, then it's only uncertainty, kind of like that. Okay, so like these were the main things regarding the active learning, and you can read this entire paper also if you want. Seattle is one of the first people to have written a survey on the active learning, and his two surveys are really popular. Like anyone who wishes to study active learning starts from his surveys. And currently there are also other methods which are based on deep learning, so you can dive those into uh, okay. And mm, there is okay, like this is essentially what I wish for this project. In the last few minutes, what I want is like I can show you some frameworks. For example, deep active learning. There are lots of papers, and then this one DPL. So it's like this is very common in the industry, the active learning, not in academia. So there are lots of methods already implemented. For example, this library, you can use these libraries also in the uh, mm, okay, and you cannot use in this project, but you can. But I would love if you could. I would love like very much like if you could look at this library. It already provides various methods, and we discuss these entropy, uncertainty with dropout. When dropout is basically when you switch off some of the neural networks, and cluster based we did k means, mean shift, and all those disagreement we did, all those adversary margin we did not do. And these libraries are very handy. There is another library for NLP thing. Mm, so this is also very helpful, and it is like kind of a very good one for natural language processing. These are the way you can have a look at this also, and there are query strategies implemented. Some of them like are really advanced. For example, badge, seals, discriminative active learning, contrast we discussed, but category vector inconsistency and ranking, all those things. So they are really helpful. Mm, Also, there is an interactive interface, Argila, which you can use to like kind of manually annotate. For example, you can select samples and use Argilla interface to provide those to the human annotator. That becomes very friendly. Fine-tuned data platform for LLMs. So you can have at look at these three libraries and feel free to play around with them. So I think that's all for the lecture, for the session, and you can. I'm open to doubts. Uh, any doubts? Mm, maybe I can wait for 5 minutes. The session is over. Maybe you can stop recording, and uh, I'm here for any doubts. Okay, nice.